Today we're going to be talking about the Doppler effect. The neat thing about the Doppler effect, it is a phenomena that relates to all kinds of waves. It is not limited to sound waves, but it typically is what we kind of first gravitate towards in terms of the discussion about the Doppler effect. By definition, maybe we can kind of read it here, Doppler effect is the change in frequency, or the appearance of the change in frequency, of the wave detected by an observer, because either the source or the observer, they're going to have different velocities with respect to the medium. Meaning this, if you were to have an observer, somewhere, and you were to have a source of a wave, and we'll start by talking about sound waves, so I think it's easier to kind of wrap our heads around. If you and the source of that sound wave are stationary, you should hear the exact frequency that's being produced. The Doppler effect deals with the appearance of the shift in that frequency when either you or the source are moving relative to each other. So if there's any sort of motion or movement between the two, whether they're getting closer or getting further apart, there is going to be an appearance in the shift of that. So consider this. Okay? Classic example is you're standing at a train station. Okay, train is approaching you, and as it's approaching you, it's blaring its horn. Now if you were at that station and you were observing the pitch of what is being produced by that horn, as it's approaching you, and you can kind of envision this because you've watched movies, you've seen lots of things where, train horn is blaring as it's passing some spot, where it goes from a much higher pitch down to a lower pitch after it passes you. Okay? The appearance of that is kind of the outcome of what the Doppler effect is. It's the appearance of that shift. Now, to kind of put it in a different perspective, but same situation, if you are the conductor of that train, do you observe any change in that frequency? No. It's the exact same frequency as to what's being produced. In the same way, if you drive your car and you're honking your horn, you don't necessarily observe a change in the frequency because you as an observer in your car and the source of that sound wave are traveling at the same speed. Okay? Now, if you're standing on the sidewalk and you have a car passing by and that's the one that's, honking its horn, you're going to observe a difference in that. So, let's take a look at what happens when we have that motion. Okay, now I know there's a lot of text up here, but I'd almost rather talk about it than kind of the textual piece of what we see. So let's take that same situation. We have the train approaching the train station, and that sound wave is being produced. Now, as it does so, because of the motion of the train relative to the observer, okay, the source of that is producing a certain number of waves per second. But with that being a traveling sound source, it has the effect of compressing those sound waves in front of it. Now, if you are an observer and you're there noticing the compression of that sound wave, that means that there's going to be more waves per second, correct? So, it doesn't take much to put that together then. That's going to have the appearance of a higher frequency sound. In the same way, when the train passes you, because it's then passing you and traveling away from you, it is elongating those waves, which is going to have the effect of a lower frequency, the appearance of that being a lower frequency. Now, I really want to drive this point home though. Does it actually change the frequency of what's being produced at the source? No. It is just the appearance of that in terms of the motion of that piece. Okay, one more thing, and I actually think that this is the more cool application of the Doppler effect, and the fact that this also applies to all sorts of different waves, even those on the electromagnetic spectrum. Now, at first, that doesn't seem like it has any significant implications, but some of our most significant scientific discoveries in the last 100 years, some of which can be kind of determined based on what we know of the Doppler effect. Now, if we were to know, let me ask you this. How many of you have heard of redshift and blueshift before? Okay, a couple of us. Now, let's say that you have a light source that is producing white light. And you know it should be producing white light. The same phenomena would apply if we were to have, let's say, you standing still, and considering the speed of light, we'd have to consider how fast that source would be moving, but that we can have a shift in the way that that light would appear to you as an observer as either being more closer to the blue side of our visible light spectrum or closer to our red side of our electromagnetic spectrum, our visible light spectrum. So, what does the blue shift mean? Okay? Now, blue is, if we kind of remember our red, orange, yellow, green, blue, indigo, violet, okay, that side of our spectrum is higher frequency light waves along the visible light spectrum. So if we have something that is producing white light and it is going to be traveling closer to us, traveling towards us, then it's going to have the appearance it's going to be slightly blue. If it's going to be traveling away from us, it's going to have the appearance of that frequency decreasing, which would push that closer to the red side of the spectrum. Now here's where this becomes, I think, of extreme significance. Years ago, many, many years ago, there was an astronomer named Hubble. Okay, many of you know about or have heard about the Hubble telescope, kind of named after Edwin Hubble. Hubble made a very interesting discovery when we actually started to point our eyes towards the sky and to study out in our universe what's going on. And what was significant about it, and I might not necessarily have the percentage right, but let's just call it 80%, 90% of what was observed was experiencing a red shift. So when we looked up to the stars, we looked out to what was there, knowing kind of what things were made of at that point. Now, it's not saying that a lot of things do have a little bit reddish color to it, but it does depend on what the actual light source do, because some stars have a little bit more bluish light, some are a little bit more yellowish orange, but a vast majority of what was out in our universe had a reddish color to it. And that meant that all the things that were observed in the universe, a vast majority of them, are traveling away from us. So, that means that our universe is expanding. Now, there are a couple of things, that would, have a little bit bluish color to what we have. So there are some things that, aren't necessarily traveling away from us, at least at the moment. Depends on all sorts of things in kind of a three-dimensional spatial field. But with that being there, that's of significance. And here's what I think is even more significant. Maybe not, we use the Doppler effect as the basis for that. But if we can take that concept of our universe is constantly expanding over time, what if we were to rewind that clock? What if we were to go backwards in time? What does that mean if we keep going back far and far enough? That means that at some point, all of the known matter in the universe probably came from one spot, leading to the theory of the Big Bang Theory, okay? Where we would have all that known particulate matter in one location. Okay? Now, I do consider that to be of significance. We actually know a little bit more about the known universe, and we can maybe talk about this at a later date, but we actually know that things aren't even just traveling away from us. If it kind of gets a little bit more weird and exciting for us, it's actually accelerating away from us. Which, as we then know from Newton's laws of motion, that there has to be some sort of force acting on all that to accelerate that away from some central point. So there's a lot of stuff that's going on, and again, we'll save the details of that discussion for another day, but just want to kind of bring that back to the foundation. It was all about redshift along what we have in the Doppler effect, okay, and the fact that all that known matter is traveling away from us. Okay, so let's go ahead. Let's talk about the math of what we have here. This equation looks like it could be a fun one, and it is. But we'll go ahead, we'll talk about it, and it's not as bad as what we need. First of all, we do have to identify, I'll come down here to the bottom first. We have to kind of identify what our variables are. Okay? FO is going to be the observed frequency. Okay? That, I would say maybe 90% of the time, is what we're going to be looking to solve for. We want to know what the observed frequency is going to be. Fs is going to be the source frequency. Typically, we know that. Okay, we would know, hey, here's what, the frequency of what is being produced. V by itself with no subscript is the wave speed. Now, I would say that for most examples of what we have, if it's not defined, we have one of two options. If it is a sound wave, what should the wave speed be? Anybody remember back to what we did a couple classes ago? There we go, 343 meters per second. So unless it's defined otherwise, if you know it is a sound wave, we should use 343 meters per second. Okay? Now again, due to the things that we talked about at that point, due to conditions around atmospheric conditions, temperature, pressure, those sort of fun things, that might vary a little bit, but if it's not stated otherwise, then any sound wave will just use 343. And if it is anything on the electromagnetic spectrum, 3 times 10 to the 8th meters per second. So that's visible light plus everything else that's in that electromagnetic spectrum that we talked about. So that would be V by itself with no subscript. Then Vs and Vo is just going to be the speed of your source and the speed of your observer. Okay? You can have instances where one of those is going to be 0. You technically can have instances when they're both moving, but please know that this is a speed and we're talking about relative speed. So their speeds related to each other is ultimately what we're trying to find. Now, most of you have probably not seen this designation before. When you've seen the plus or minus, well, everybody here has seen plus or minus before, but the thing that you might not have seen is minus or plus. Okay? Now, understand it's just the flip of that ratio. And you're choosing one of those, not both. Okay? Just like it would be plus or minus. Now, here's the thing. In this equation, between the numerator and denominator, you will never have the plus piece in the numerator and the plus piece in the denominator. In the same way, you will not have negative in the numerator and negative in the denominator. So it's always going to be the opposite sign. And the way that I have it memorized is I memorize what happens with the numerator and then just flip the other one. Okay? So that's kind of what we have down here in the bottom of the note. So in the numerator, the plus will be used when the observer and source are moving closer together. And the negative will be used when they're moving away from each other. Okay, so then whatever we use up top, we're going to have the opposite sign below. So if it is plus up top, then our first option would be, our only option is minus on the bottom. Okay, if we have minus up top, it'll be plus on the bottom. Okay, so whatever the opposite operation is going to be, that's what we're going to use. All right. So we'll do a quick sample problem here. A siren mounted on a tower emits a sound whose frequency is 2,140 hertz. A person is driving a car away from the tower at a speed of 27 meters per second. Speed of sound is defined here, and it is kind of what we've used before, which is that 343. And then we're going to go ahead and figure out what frequency does the person hear for the sound. So what are we trying to solve for? FO, our observed frequency. Okay? What is our source frequency? Okay? 2,140 hertz. Wave speed? 343 meters per second. Our observed velocity? Observer's velocity. Okay? That is our 27 meters per second, and our source velocity should be 0. I hope that if this is being emitted from a tower, that that tower is not moving. Okay? All right, like everything else, let's go ahead and let's set up our equation, and then we'll go ahead and do our substitution. Okay? So we're looking for our observed frequency, so it's going to be our source frequency times. We're going to use a bunch of parentheses up here, so let's kind of put it together. So open parenthesis in our numerator. From a variable standpoint, do not tell me substitution yet. Let's work on what the numerator is going to look like. So what are we going to start with up top, since these are traveling away? So 1 minus, okay, then what's the ratio of what we have next? No, not numbers. What's our variables? What are we plugging in? VO over V. Okay, that would close that off. Close that off. Then in our denominator, this would be 1 plus the ratio of Vs over V. Closed, closed, and then close that all out. Now we can go ahead and do our substitution. So this would be our 2140, open parenthesis, 1 minus the ratio of our observer velocity, so 27 over 343, closed, closed, divided by, open, 1 plus our source velocity, 0 over 343, so that piece of it would be easy, closed, closed, closed. Go ahead, take a moment and calculate what that response should be. And anyone who's got it, what do we get? Okay, I lost you for a second there. 1971, and you said it, that would be in hertz. So here's the nice thing that should be an easy check for us. Check your final answer. We're traveling away from our source. We get a frequency that is lower than where we started. Does that make sense? Yes, okay? And let me just take a very quick moment to kind of explain what exactly this equation is doing for us, because there's a lot of stuff going on. So we start off with what we have here, the 2140. All the stuff that's in here in parentheses is just helping us to figure out by what amount that frequency needs to change, okay? And so when we do the 1 minus the ratio of 27 over 343, that's just giving us kind of a ratio, if you will, of based on those relative speeds of what we get, and that's why we get that here. So point being, please just check this to see, are we getting the appropriate change? Are we getting larger or are we getting smaller based on what we initially had? Because if this was a situation where you were traveling towards the source, if you were to calculate that same answer, we've got some concerns because we know that that is a decrease in frequency. So that, I say, would be your greatest check. Any questions here?